Okay, cool. Hi guys. I'm Niyati. You'll probably know that. I'm in my second year and I'll be talking about evaluating and inducing dialectal robustness.
You talking about it a little loud?
Yes, I will try to be a little louder.
Thank you.
Great. Cool. So there are around 7,000 languages in the world, and we want to do NLP for all of them. And this is hard because many of them are very low resource and we can't collect data for all of them. Luckily, a lot of this diversity is well structured, and that means we understand pretty well how languages differ from each other within language families. Right, so I'll be talking about two of my recent papers today that explore how we can exploit this idea, both to evaluate dialectal robustness as well as to induce it in machine translation models. Okay, so this is the first one. It's called evaluating large language models along language variation. And yeah, so we said already that most languages in the world are low resource, but have a closely related high resource language neighbor. And we have some evidence that LLMs show some extent of cross-generalization, right? So if they're trained on some high-resource language, they have like some non-trivial performance on closely related low-resource languages, but this usually comes with significant performance degradation, and we want to do something about that. So in this paper, we're interested in what it is about language variation or the differences between languages that cause this performance degradation. When a model is trained on one language and tested on another one. And we consider the following kinds of differences between closely related languages, right? So we're interested in looking at different dimensions of language variation, and we have phonological change, so sound changes between different dialects. We have morphological change that's concerned with like affixal changes, and then lexical change. And we divide up lexical change into two types, right? So that's functional word change, and that's changes in like closed class words, basically. So pronouns, determiners, appositions, those kinds of words with like grammatical functions usually, and then non-cognate content word changes. And the reason we do this is because of the intuition that these two classes of words differ in how they vary across dialects. And so that's what we want to do, and we can frame this as a question of studying performance degradation as a function of each kind of linguistic distance, right? So if we can measure, or like if we can quantify this linguistic distance, and if we could do that, then we would be able to do these things, right? So we would be able to estimate performance degradation for a new language for which we didn't have evaluation data, but we knew like what its linguistic distance was from some HRL. We would be able to like understand performance degradation a little bit better. So like what kinds of linguistic distances contribute most to it. And hopefully that would also give us insights on how we can fix this for low resource languages.
Sorry, just a quick question. So when you say linguistic distance, between what and what?
So we have a model that works well for some high resource language, and we want to make it work for low resource languages that are related to it. And so we're interested in like linguistic distances between those two languages, because we observe that while the models still work for related like low resource languages, they show a good deal of like degradation of them.
So there are many things that can affect the performance of the language.
Yes, exactly.
Which include how much training data you have for it.
Definitely.
And how intrinsically difficult the language is.
Yes.
Like maybe there are some languages that are actually harder for humans or harder for LLMs or something.
Definitely.
It express less information. So are you fixing all those things? So is the question like if you have you're going to train a small amount of Tagalog, and then you're going to train on 10 times as much of some other language, and you get to pick that language to be close and far away.
Yes, so that's so what we're going to do is actually set up this study on artificial languages, and that lets us control all of the things that you talked about, right? So we know for sure that they're all unseen, and we're talking about zero-shot performance.
Okay, I mean, I'm sure also at the setup is, but are you going to hold the test language and amount of test data in that language, or sorry, amount of training data in that test language fixed?
Yeah, well, this is all zero shot, so there is no training. Like all of these are unseen. Yeah. And yeah, I mean, so this is what we do, right? So we
Related question, to this, which is that in real life.
Yeah.
The only reason for degradation may not be the language difference. It could be genre, it could be style, it could be topic, it could be any number of things.
Yes.
I heard you say synthetic languages. There you can actually control for those things. But is there any? Well, you can tell me more how you're going to deal with that in real life.
Yeah. I mean, a lot of things.
You can tell me later.
Okay.
Looks like you're going to do synthetic stuff.
Yes. Yeah, basically that's what we do, right? So we have generative models of linguistic noise, or like linguistically principled noise. And what that means is that given some word in our HRL, we use this model, or we call it a noiser, to create like some noise version of this word that looks like it might belong to some dialect of it. And these noises are parameterized by these like Bernoulli thetas, and these thetas serve like as a proxy for linguistic distance, right? So you can dial them up and down and get dialects that are more or less distant from the source. And we can do this for each dimension of linguistic noise that we talked about, right? So yeah, so this lets us quote unquote translate HRL val data into these artificial dialects that are at like varying distances from the HRL, and then we can go ahead and find this function that takes us from linguistic distance or theta to performance degradation. Right, and so yeah, so let's talk a little bit about what these noises look like. Briefly, we said that they are parameterized by these Bernoulli thetas, and theta is just the probability that we noise some unit in the source language, and what that unit is depends on the kind of noiser that we're interested in, right? So for the phonological one, it would be phonemes. For the morphological one, it would be affixes, and so on. And these noisers are loosely linguistically motivated. And what that means is like we, for example, would only generate sound changes that were likely or observed in the real world. And similarly for the other ones. I think like if anyone is super interested in any of these, we can talk about those later, right? And these are just examples.
You resort word order.
Yeah, so we don't do any kind of syntactic noising at all. And yeah, we have some reasons for that. But essentially, like syntactic noising is very hard to put into this sort of framework of like gradually increasing distances in a dialect continuum, because it usually changes at like larger boundaries between language families.
That's right, it's control.
Like syntactic differences are difficult to put into this framework of direct continua, because they usually like there are very few called syntactic principles, and they usually change at like boundaries of language families rather than like gradually within language families, I guess.
There was actually a dissertation done here 5 years ago.
Yeah.
On synthetic languages with syntactic changes, so you could actually maybe combine.
Yeah, I think I saw you're on one of those papers. Yeah.
Yeah, we said question.
Okay. Yeah.
Can you go back to the previous slide?
This one?
Yeah. I guess we'll talk more about all these kinds of changes. When you say noise suffixes, do you mean that you noise up the existing site, like you replace?
Yeah.
You use the wrong suffixes sometimes. Okay.
We basically have a new inflectional paradigm for the language. It's not like we replace one suffix with another suffix in the same language, but we just generate a whole different inflectional paradigm for our artificial dialect. And we map like some suffix in the original dialect to a new suffix in the new dialect, which is kind of maybe what you can think happens in a for two real dialects. Right? They just have different inflection.
Okay. You'll be talking about this, I guess. Actually,
I might not, because I didn't have time for that, but we can talk about it. Yeah. Okay. So now we have a way to generate this hypothesized dialect continuum for some HRL, right? So we have thetas, we can increase them, and we can have this like artificial dialects at different distances from our HRL. But crucially, like we want to be able to place real languages within this space, right? Otherwise, you're just doing a bunch of stuff with artificial languages, and what does it matter, right? And being able to do this matters for like quite a few of our goals, right? So for example, we want to estimate PD for real language, for which we don't have eval data, and we then need to know what theta that real language was generated by, I guess. So this was our setup, and we don't have eval data for a low resource language, but what we can assume that we do have are these lexicons over here, right? So like bilingual lexicons and small bytext are available for like hundreds, if not thousands of those languages. So we can assume that we have them, and then we can assume that our dialect was generated using some underlying thetas, and we can do like a posterior computation on our with our noisers to find what these underlying thetas were. And you need bilingual lexicons to do that, but like I said, that's not an unreasonable expectation. And yeah, in some more detail, we said that our noiser affected some unit Q with some probability. And so all we need to do to find posterior is to like just count how many times the source unit was affected over all units in the high resource language. Right. And there are some like complications. Real languages have all kinds of noise together. Right? It's not like they only have morphological noise or only phonological noise. So we need to be able to do this. We need to be able to find posteriors for individual noisers, given that they are like composed, I guess, in the new language. But I think I might have skipped this slide by accident. But we had, I had a note here that said that we can just compose all these noise types in the same, like within this framework. And as long as we apply them independently of each other, we can do posterior computation for each individual kind of noise, basically in the same way.
I'm sorry, when you say overwrites here, you mean like one-to-one substitutions?
No, so sorry, so that maybe wasn't clear, but what I mean is that if we want to compose all these kinds of noise, it might be that the phonological noiser affected like some part of this word, and the morphological noiser comes along and also affects it. And in that case, we'll just let the most recent noiser override the previous change. And the point over here is that even if we allow that, our posterior estimation is still okay, as long as all the noisers were independent of each other. Yeah.
Is the noise application itself sequence independently, while you use the orders, realizing the same final lexical form or regulative combination?
You might not, right? But the idea is that we kind of have good intuition for why these noises should be applied in this particular order. So lexical change, for example, is much more. Yeah, we just fix an order and we say we always do it this way, because lexical change is very dynamic and sound change maybe less so. So we always do like lexical change at the end.
So what do you mean that final independence is not just while independently and concurrently, and we can apply in sequence?
Yes, so yeah, that's good.
Whether or not to change something in the stochastic one which is made independently.
Yes.
Would that noiser at another position than what other noisers before and after?
Yes, that is what I mean. Thanks.
Yeah, I still don't get the point about MLE estimates, but maybe it's not threshold that I understand.
I mean, it's yeah, I can explain that, but it's I mean, one might be worried that because we are overwriting different noisers, we would be unable to get a good estimate of, like, say, the first noiser that we applied, because the changes that it made were like now vanished. But I guess this is just a note saying that we can still do this because of the way that this posterior composition.
I mean, I think my uncertainty might have originated earlier with the title of the slide. So what is it a posterior over? There's some hint in the last bullet point, I think.
You mean this one?
Use theta.
Oh, okay, yeah, sorry.
Yeah.
So the idea, just to make it
Yeah.
very concrete,
Yes.
one of the noises you might apply is convert all long R's to schwas. Another one you might apply is delete a word final schwa. And what you're saying is it doesn't affect the MLE because long R's will be made into schwas with some probability and final schwas will be deleted with some probability, which are independent with one like the product form.
Exactly.
And that doesn't, therefore you can compute your data.
Yes. Exactly.
In your example, though, I don't understand, how,
In my
in your example, yeah. So you just said that, some of the R's are turned into schwa and then deleted. So if you don't have a schwa at the end, how do you know if there was one to begin with, and how do you know if it was formerly an R? So like your rate of turning R's into schwas will be obscured by the fact that some are deleted.
Yeah, that's independent, that when the schwa deleter comes along, it doesn't worry where the schwa came from.
No, I understand that's independent, so I don't think you can get back the parameters.
Oh, I'm waiting for it to explain how that happens.
Yeah. So the reason we can still do this is because when we do posterior estimation for composed noises, we first make a decision on which noiser that particular change originated from. And that means that if we were dealing with, like if we wanted to find the phonological posterior, we would basically, and we looked at the word and we said, okay, like this suffix has been messed with, probably by the morphological one, then we don't look at the suffix at all, which means we essentially disqualify all of these, we disqualify parts of the data that were affected by subsequent noises. And that means that basically you're.
Oh, sorry, do you mean you don't only see the final result, you see the intermediate result when you do the estimate? I guess I don't know if the observable, sorry.
Yeah, we can't see the intermediate ones because we're talking about real languages. So we're just looking at real languages and we're saying like, okay, what are the different, what are the parameters of these different noisers that generated this real language, like this real dialect, from its highly source language neighbor, right? So we don't actually observe any intermediate states, but we are still able to find these. Yeah, sorry, I feel like I'm not being clear at all.
Yeah, I mean, maybe you should just go on, and I'll see if I can.
Okay, maybe.
Sort it out for myself.
Yeah. So yeah, here are the languages that we work with, and here are the low resource languages that are related to them. And then
So German has English. What is German?
it's Swedish.
Swedish.
Yeah. So these language families, like these dialects, really differ a lot in how much they're close to the HRL. And of course, like Swedish is not really a dialect of German at all, but we're thinking of language continua, right? So
I don't think are these dialects.
yeah, these are different.
Okay, but you're dealing with written form.
Yeah, so a lot of these dialects won't show like variation that you hear in dialectal Arabic, and that's definitely a problem. But yeah, we are concerned also eventually with
You're going to show us a bunch of results, like numbers of. And we'll see some terms.
yeah. These are all like basically what's available in Flores or was at the time. Now we have a bunch of stuff. Okay, so I'm gonna show you a bunch of results that look like this, but just on how to read these. So the caption has the task and the noise type. Also, this is machine translation, this is XNLI, and this is X story close. And then on the x-axis, you have theta. And that depends on the noiser that we're dealing with, right? So this is theta f, this is the lexical function word noiser, and the y-axis has performance degradation relative to the HRL. And then you have different languages in different colors, and you have the trend. This trend in black is the mean performance degradation over overall languages. And I'll come back to these and we'll talk about we'll talk about what we see from that. Anyway, so these were our goals in the red, right? And here are the questions that we might want to answer with our computer trends. So firstly, like we want to use these trends to say things about real languages. And we've shown that we can compute these posteriors for real languages to place them within this distance space that we set up. So we want to see whether trends on real languages follow the ones that we computed on artificial languages. And then we also want to understand like what kinds of linguistic noise are most damaging, or what is the effect of the task that we're doing on these trends. And then we want to keep in mind that the goal is to eventually treat performance degradation.
Since your application is translation,
Mhm.
I'm guessing that what you'll do is you'll reduce the corpus first. But you won't do anything like try to induce new subword units or anything.
So for this paper, we're looking at 3 tasks. Sorry, that slide was a while back. But yeah, machine translation is one of them. There's also like the classification tasks.
Okay.
But yeah, we're just using the noises to like translate to basically create new eval data. And we're just directly evaluating on that data zero shot without doing anything.
Okay.
Yeah. And no, we're not like messing with the subword vocabulary or anything of the ocean, because there's no training involved.
So what I can imagine in a real life setting is that you may not have any other text if you're doing translation.
Yeah.
Interest. But you may have a monolingual text and you might induce DPEs jointly. So there is some hope that something reasonable rather than break up the target language eval set with some weird way single letters and then that could be it could be a cause of the degradation, but it wouldn't be a cause that you couldn't mitigate.
That's true. Yeah.
All right. Just making sure I follow you.
Okay.
I don't know yet.
Oh, that's fine. And yeah, so we want to look at whether the trends on the real languages follow the ones that we computed on artificial languages. And so for the low resource languages and tasks that we do have data for, which is just empty, this is all Flores, we can plot the observed performance degradation against our computed posterior data. And then we can look at whether we get like roughly similar trends as the ones that we compute on the artificial languages that are showed in black. So ideally we would want these trends to look a little bit similar, and they do, which is a good sign that our like noises are capturing something that is useful in understanding performance degradation. And we also, well, this is a note that, yeah, I don't think we have to go into this, but yeah, we would expect that observed PD would always be higher than the one we predicted, because again, like all the real languages have different kinds of noise that are all composed together instead of these like individual noises over here. But whatever, that's fine. So we now want to interpret our results from like different angles, right? So we want to look at the effect of task and noise on performance degradation. And so for the task, these like the task is on the columns, right? So that's empty, SNRI, and it's very close. We kind of see that these trends look similar across tasks, and also the trends are all roughly linear. The main, like I guess the most interesting difference across tasks is that the variance in performance degradation given language and given data is much higher for the classification tasks than it is for ND. And that has a pretty natural intuition. It just means that or rather, it indicates that the classification tasks are very sensitive to whether specific words are noised. as opposed to empty, which degrades more smoothly given theta. Okay. And then we're interested in looking at the effect of noise type. So we can, like, the way we can understand that is by looking at, by comparing slopes of these different noises with each other, right? So the higher the slope, the more damaging the noise. That is, like, the higher the performance degradation we get in making like some small increase in noise. And yeah, these are all lexical noises, and the one on the top is just function word noise, and the rest of them are content word noises, right, with different like sort of fixed levels of function word noise. And I guess the first thing to see is that content word noising is much more damaging than function word noising, which is unsurprising. But we also note that function word noise still causes a decent amount of damage at natural levels, right? So what do we mean by that, right? Like these languages, like these posteriors, I guess, languages give us a sense of where, like, what is a natural range of theta that we expect, and we see that even within this natural range, it still corresponds to like a non-trivial amount of performance degradation. And this suggests that function word noise is still like a player in mitigating PD, and we'll come back to this idea. And then these are the phonological and morphological noises, and we have, I guess, like similar observations. So the phonological noise, again, this sort of range of noise still corresponds to a decent amount of performance degradation. And this is less true of the morphological noise, which is nice, right? So all of these languages are here on the left, and that is relatively a lower amount of degradation as compared to the other kinds of noise types. And that's nice because it means that models are generally able to capture important information from word stems or from context. Anyway, so in summary, we set up a method to model hypothetical dialect continuum for some language by simulating like mechanisms of linguistic divergence. And this lets us study zero-shot cross-lingual generalization on truly unseen languages in LLMs. And in general, what we find is that language distance is predictive of PD, and yeah, like some kinds of function word noise and phonological variation affect LLM performance maybe more than morphological change.
That's right. When you say performance, you don't mean on the log loss, but some measure of MT, like what?
Yeah, exactly. Okay, so I had another paper that I was going to go through, but what I'm going to do is do that on another day because we have Ritika. What? No, I think just present, and I'll do the second paper on another day.
Are you sure? Because I can also just add more content and do it on another day. Which is what I'm talking, because I cut back on content.
If you want, I guess.
Other things equal, variety is nice.
Yeah, it's just that if I get more time, I might as well just, use that to add back whatever. I had made the assumption that I would have like 15 minutes, so initially I thought it was 20, so I already cut it back. I mean, like, it depends on you.
Okay, I'll just finish and you can do yours.
Can you ask a couple more questions?
Okay, sure. Yeah.
So one question was, you have this list of changes, right?
Yeah.
When you apply them and produce this language, the data is based on estimating on the real language. Do they look similar at all? I mean,
The actual languages?
Yeah.
Okay.
And
Yeah.
for example, if you build a simple discriminator, you'll be able to tell whether it's the fake sentence or the real sentence from, I don't know, you need to classify it. So would your Bhojpuri data, whether like you can reproduce things that look like Bhojpuri or not. There
Uh,
are slide with examples, I don't know whether they were synthetic ones, you had like 5 or 6 pairs of sentences.
so hang on. One sec. I have another slide that has what you want. But I need.
Yeah, the reason that I was thinking that a lot of these changes are contextual changes, they're not contextual changes.
Yeah, I mean, I think like any classifier would be able to like tell immediately. But I think crucially, so that is something we did think about, like do the generated languages look similar to the ones like to actual languages? But I think the main goal was that even if they don't, as long as they produce similar patterns of how much, like similar patterns of performance from the model, they are still useful because they let us say things about how performance changes. But I do have slides with actual examples, and I can put
I
that.
think you answered my question with the first order. Thanks.
Okay, cool. Yeah, we can find that slide later somewhere. And okay, we looked at understanding what affects performance degradation, and now we want to do something about it. So this paper is called DialUp, Modeling the Language Continuum by Adapting Models to Dialects. And dialects to models, that's a long title. And yeah, we already talked now about how a good part of dialectal variation is systematic and how it's useful to think of languages as lying on a continuum of changes. Whoops. And we've talked about some of these kinds of changes. Right. And so now we want to use these ideas to adapt pre-trained models to work on language continua of training languages, including on unseen and unknown target dialects and variants, right? So we might not know what kinds of dialectal inputs we get at inference, but we just want to make our model more dialectally robust. And now we're working only with machine translation, and we're assuming that we have a model that is good on the high resource language. We're assuming that we have bytext in the high resource language and the target language that we want to translate to. And in this work, that's going to be English. And then we can say that, well, maybe at inference time, we do know the input language that we're going to get. And then we might have lexicons in that language, which again is a reasonable assumption. So how does this work? DialUp is a dual technique for improving dialectal robustness. And so the idea is that this is a domain mismatch problem, right? So the model understands the high resource language, but the input is the high resource language plus some dialectal divergence. And there are two things we could do. So like we could either make the model familiar with these dialectal mechanisms of divergence, or we could take the input data and try to remove this divergence in some way at inference time. And so we call the first method MTD, like model to data adaptation, the second one DTM, right? Data to model adaptation. And this is MTD. We have this model, we have our HRL target bytext, and we already have a good way to model our dialectal mechanisms from 15 minutes ago, right? And if you dozed off, that's fine. The main thing to remember is that we are able to take using some linguistic principles, generate a bunch of data that looks like it might belong to some fake dialect of the language. And yeah, at this point also, your question becomes pretty relevant. Do the artificial dialects that we generate look similar at all to real languages? And we don't know, but I guess we tried doing this and saw what happens, right? So we can fine tune our model on this data now, and then we can hope that when it sees actual dialectal data, it'll work on it, right? And yeah, here are these same examples again. And then this is the other side of that. So we want to now go the other way. We have our model and we have these lexicons, we have this input, and we can just say, okay, like if our model is good at the HRL, why don't we just make our input resemble the HRL as much as possible by swapping out dialectal words for HRL words. And hopefully that'll work better because the model now says more words that it understands in the input. Okay, so we are still separating out two classes of words, and we have function words that are a small set. They are very frequent, they are much more dialectal, and they're easier to align. And content words, have different characteristics, right? They're open class. They are difficult to collect bilingual lexicons for because there are many, and they're much harder to align and much more difficult basically to have for low resource languages. Okay, so yeah, so these are just examples of what it looks like when we apply this denoising, as we call it, right? So on the top, that's function word denoising, we're switching out words like the, has, do, whatever. And then content word noising switches out content words, and then we can also like combine both of these and change whatever we see in the input. And then we can combine these two paradigms, right? So we can do model to data adaptation where we end up with this fine-tuned model over here that is supposed to be good at like general dialectal input. But if we do know the input dialect, we can also intervene at inference time. And these two methods have different advantages, right? So the first one doesn't need any knowledge of the target dialect, and the second one is completely training free. Okay, so these are the baselines that we compare against, just the model off the shelf, or we could fine tune on it like the same amount of HRL data, or we could also have like some random noise, right? So we're claiming that like our model of linguistic noise is good for the model, but what if we just did like some random perturbations? Would it work just as well? That's what we want to test.
Sorry, well, I'm a little confused. I thought your synthetic languages also involve random replacements. And so the question is, what is more random in the second case? Are you saying instead of inserting a suffix at the final position, you insert it in the middle? Or are you saying that it's a different suffix every time, or?
Yeah, so our noises are also random, but the outputs, like the things that the replacements they make, we said are guided by some principles, right? So if we're switching out a T, we don't want to replace it with like an H, for example. We probably replace it with a D, because that's a sound change that you see very often, or like a TH, for example. So that's one thing. The other thing is that, yeah, exactly as you said, like when dialects, we often see changes at the ends of words, because like inflectional, derivational paradigms change, but cognates usually maintain stems. Stems of like the bodies of words, I guess.
Okay, so let me see if I understand. You have a system that makes a synthetic language, and it draws some parameters realistically, and you're going to draw them from different distributions in the second case. It's random in both cases.
Exactly.
And so if you were using a bad distribution, like a more uniform distribution or something in the second case. Yeah,
that's a much better way of putting it. And these noises are just picked from the literature. So people have tried doing this in the past, trying to make empty models more robust. And what they usually do is like replace characters with random characters or replace words with other random words in the vocabulary. So yeah, that's what we compare against. And then once again, here are the language families that we study with the high resource languages in the center, and all of these other languages. These languages really differ from each other in a number of ways, right? So some of them are really high resource already, like Spanish over there. And they also differ in how much the language families themselves are diverse, right? So the Austronesian language family, for example, is really much, much more diverse than some of the other ones here. So I guess that's an important thing to keep in mind when we look at the results. And we are working with two models, M2M 100 and IA. The first one is sequence to sequence multilingual MT model, and the second one is multilingual LLM. So we have two paradigms here of machine translation, and we want to test our methods for both of them. And then, yeah, just data sets we use, we are testing on Flores and Creole MT, which is a data set for Creole languages that Nate worked on. And yeah, we use bilingual lexicons from like Penlex, Swadesh, and we align them ourselves from Flores for the function words, because I think like mainstream lexicons don't include those usually. Okay, so here are the results by language family, right? The blue bars are M2M, the red ones are IA. The y-axis has improvement over the best baseline. So the best baseline could be any one of these three, like, and we show the improvement of our best method. And the method itself is indicated by like the filling or the hatches inside the bars, right? So in general, I guess we see that DialUp helps for most language families. And then we see that some languages benefit a lot more, right? So these, some languages benefit a lot, right? This is like plus 15 to 17 blue points, which means that we're going from basically garbage to something decent. But we only see these, like we also have these CRLs over here that benefit basically not at all. These languages, by the way, are ordered by their baseline performance. So the ones on the right had a much lower initial baseline. And in general, we kind of see that languages with lower baselines benefit a little bit more, like more than ones that were performing well to begin with. And then we obviously see, M2M gains a lot more IA, which is unsurprising. And then we see that these gains also depend on language family. So for example, Indic and Romance gain a lot more than like Arabic or Turkic. And then finally, just combining both of these approaches does the best, or does better than either in isolation, which is nice to see. And then we can look at these paradigms, like we can try to compare MTD, DTM, and the combined method from left to right. And this is like the spread of gains by language for each language family for these three paradigms, right? And in general, we see that MTD helps for most languages in the family. So we don't have many languages that actually degrade if you just do MTD. For DTM, that is clearly not the case, right? So we have some languages that really degrade if you do DTM on them. And these are usually high resource languages. So yeah, if you consider Italian your HRL and you're working and your dialect is like Portuguese or something, and you switch out Portuguese words for Italian words, that's really gonna hurt, which is again not surprising. But the good news is that you can switch off DTM really easily. It's an inference time trick. So the other interesting thing is that DTM for function words is much better than DTM for content words. And yeah, this sort of, like we pointed out, function words are important and they contribute a lot just by themselves to
And the Jabberwocky, right?
yeah, exactly. Yeah, so the other thing that contributes to this is that function words are a small set and they're easy to collect like really clean lexicons for, as opposed to content words more. So those are noisy, and that means we like end up introducing a lot of noise when we try to do DTM with content words. And that is like hurtful, especially for higher resource languages. Okay, and then super quickly, these are, we just looked at some of these outputs to understand that the dialect helps in the way that we intended it to. And in general, we see that, yeah, like most of the improvements come from treating these cognate phenomena better, where the baseline kind of breaks, either produces gibberish or reproduces the input, or does like transliteration or something, and DialUp is able to like decipher these, I guess, dialectal changes on them. And then we are also interested in, so like I said, right, we have a bunch of CLLs and they're all very diverse in their characteristics and like how low resource they are, or how much they differ from high resource languages, or what initial performance on them was. And yeah, like we find that baseline performance is the most important predictor of gains, right? So if the language was performing badly to begin with, it's much more likely to gain from our methods. And that next, its closeness to the high resource language matters in an interesting way, right? So if it's too far, that's not good. If it's too close, that's not good. But that's basically like a middle spot. And that's also not too hard to answer, right? Like if it's too far, then you probably have a lot of non-cognate phenomena that our method can't help with. And if it's too close, then it probably already does well to begin with. So we have this kind of curve. Yeah, finally, we also want to look at why like DTM is hurting for high resource languages. And yeah, I think I already mentioned this, but lexicons are usually bad for most languages. And that means that DTM introduces a decent amount of noise. For low resource languages, that actually doesn't matter as much because performance on those is so bad to begin with that even like information that you introduce that is not noisy still helps a lot. But for high resource languages, that matters because you were already doing fine to begin with. Okay, and then some language families don't gain as much as others. That's Arabic and Turkic. These languages are morphologically rich. They have fewer standalone function words that we can replace with our methods because our methods are based on like white space splitting and don't have, more sophisticated morphological tools to identify these morphemes, I guess, in these languages. And therefore we just make much fewer swaps on these languages. And so we just don't see much gains. And then, yeah, that's it. We introduced this dual technique for dialectal robustness, and we hope that people use it. And yeah, these are just some next directions, but that's all.
So in DTM, can you evaluate sort of running through the MT system, how well the high resource language is being reconstructed?
Oh,
like you're basically saying, given access to some lexicons, if I understand correctly, there's other ways to do it, but yeah, I think you have some heuristics that look at gold standard lexicons.
Yeah.
And say, okay, transform the input from English prime back to English or whatever it is.
Yeah, and
So is it doing a good job?
We just look at like the only way or we do it is just, oh, actually, this is not even the right table. Oops. No, actually, yeah, this is fine. But the only thing we do is we look at percentages of words that were swapped out. So we just say that, we just try to find like what was the coverage of our bilingual lexicon over the dialectal input. But we don't directly measure what you.
Yeah, it's just like you could do a final grade thing. If I understand right, every sentence of English prime was derived from a sentence of English. Which we then apply modifications to. Is that one?
So over here, the input is just an actual language, right? Like it could be.
I'm sorry. Okay, this is not with synthetic language.
No.
Yeah.
So now we're just only working with improving performance on actual languages. In this, and
do you have any examples of what it looks like to try to take Is that version to Italian or something like, I don't know, the.
Yeah,
Like, I'm
so-
doing the dialect.
Hang on, I have
And
maybe.
it'd be great to see it for English, so we can all understand it, but.
So this, for example, I think on the top is,
On the top looks like ordinary French, and on the bottom is some dialect of French that I don't know.
I think the bottom is Italian, actually.
Sorry,
It's Italian,
oh, the bottom is Italian, yeah, right. Okay.
yeah,
So is the idea that you're trying to, in this picture, you're trying to turn French into Italian or the other way around?
French into Italian.
Got it, okay,
And we are treating French like a dialect of Italian.
yeah, basically. Well, it's all modern dialects of Latin.
So yeah, this is basically what we'd end up doing with this approach.
One thought I would think that if you think about what you're doing with your runtime
Mhm.
version, but you're basically doing cascaded translation.
Definitely.
So did you think of just like, you have a lot of good high resource language and you have some method for converting it into this low resource language synthetically to be the first one. So we just use that as parallel text. It translates the low resource text into high resource. Now, of course, all the input text is fake.
Yeah.
But it doesn't matter. And then use that in a cascade. So
Yeah.
now next time you get a real, in this case,
You get something like
French
this.
sentence.
Yeah,
Even though you're trained on this fake Italian to real French translation.
yeah,
or the other way around.
yeah. David wanted to do that. That was me time. But that's a good idea. Like there's,
A lot of that is because if that, and at least on the high resource side, you have the effect of having had a large molecule.
yeah, no, I think, and there,
More than only large, good high resource text. Whereas the low resource text in the training was fake, of the translation.
right. Although over here, we are not doing translation. Yeah, just,
Replacement.
yeah,
which is,
no, I understand.
Code managed translation.
No, there are definitely more sophisticated ways of taking a low resource language and trying to make it as close as possible to. Yeah, I mean, thing we do, like we have bad empty systems, right? Even if they're bad, we could use those as an initial, like a starting point, and then plug it into or whatever. That's another thing we could do.